We would like to know how to describe a traveling wave in a form of an equation. And so let's take an example from our textbook. Here we have a traveling wave, and the thick red line is at t equals 0. So this thick red line here, it's kind of hard for me to trace this, but hopefully you get the idea. And after a certain amount of time, t, then the wave has moved to this point with the dashed line. We need to know how to describe that. Well, we have a wavelength, so we have a distance, and this is the x direction. So we're going to have some distance variable plus some time variable. So we'll call our wave equation d, and it's going to be a function of two variables, x and t. And we'll start, it's going to have some amplitude. Now you notice that the original wave was starting with the wave going through the origin. And so for an oscillating wave going through the origin, that's going to be a sine function. And we know our wavelength is lambda, and lambda is the complete 2 pi radians. So our factor 2 pi divided by lambda gives us the ratio for the wavelength. It basically compares the radians to the wavelength. And then we're going to multiply that by x minus velocity times time. So our wave velocity is the distance, or the velocity at which the wave moves. And notice that it's going to the right, so we're doing a negative sign. If it was going to the left, we would do a plus sign. Now, this 2 pi divided by lambda can be distributed through. I will have 2 pi x over lambda minus 2 pi velocity times time over lambda. Remember that velocity is equal to lambda times frequency, and that would be also lambda over period. And this is velocity divided by lambda, so if I bring lambda under the velocity, I get 1 over t. So this can then be changed, this last equation can be changed to 2 pi x over lambda minus 2 pi t over the period. Or we can also write the amplitude times sine of 2 pi x over lambda minus 2 pi frequency times time. And we will generalize this statement, this equation, with another k value. And that will equal a sine. And we're going to use the variable k subscript w times x minus omega t. Where k of the wave, and I'm always going to try to do a subscript so that you know that I'm talking about the k of the wave and not the k of the spring, is equal to 2 pi over lambda. And of course, omega is equal to 2 pi frequency, and that's also equal to 2 pi over the period. Now, an interesting relationship can be found by taking a look at the velocity is equal to lambda times frequency. And if I swap k of the wave and lambda, I'm going to get 2 pi over k of the wave, and frequency is just equal to omega over 2 pi, and that just tells me that the frequency is omega divided by the k of the wave. So this description of a traveling wave equation shows us that from the equation itself we can come up with the velocity. We just have to look at the coefficients of the x term and the t term, and we can calculate the frequency immediately. And this equation, remember, is in two variables. It's in space and in time. You have to have both of those to be able to come up with the correct location and the correct where the peaks are going to be. This is kind of idealized. They kind of just moved it over, but this x value could make it so that these peaks are in a weird way and a different configuration than just looking like it slides over. So don't want you to get confused that all of them are going to look exactly like this. You might get some that are shifted a little bit differently that doesn't look so symmetric.